Hello guys, I am Galias Taka. Welcome to Quality and Welding Metallurgy. Today we are discussing on Welding Austenitic Chromium Nickel Stainless Steel Piping and Tubing Part 2. Ferrite. Weld metal structure, the microstructure of austenitic stainless steel weld metal in the welded condition is quite different from that of the root base metal and alloy, has a major role in controlling cracking tendency, mechanical property, and corrosion resistance. Those alloys are sluggish in their cooling transformation because of presence chromium and in the as well condition exhibit some metastable delta ferrite in the structure. In root product, this phase usually has become transformed to austenite, and these steel are thus non-magnetic as supplied by the mill. It may come as a surprise at first to find the austenitic stainless steel may be magnetic, especially this is autogenous GTAW or TIG welding on non-magnetic base metal. The delta ferrite formed in the weld metal at its solidus temperature, freezing point, and persist down the room temperature untransferred. The quality present, the quantity present in principle determined by the composition of weld metal. By varying the composition of the filler metal, weld metal can be made completely austenitic, such as with type 310 weld metal, or partially ferrite, such as with type 308, 309, 312 weld metal. Since some stainless steel filler metal meeting all application specifications, requirements such as 309 and 316 are supplied with some or even no ferrite, or with typical ferrite number Fn of 4 to 10. This ferrite content of austenitic stainless steel filler metal should be considered when they are ordered. This ferrite phase, the attention given to ferrite here in a indication of its importance in the soundness of the some stainless steel weld metal, as well as subsequent performance of the weld metal in surveys. Ferrite has 8 major effects in austenitic stainless steel. Full austenitic well deposits are sometimes prone to crack. This susceptibility seems to arise from the low melting constituents compound of phosphorus, sulfur, silicon, chromium, Cb, sometimes called niobium, other elements that make up the grain boundary in the final stage of solidification of the weld. Delta ferrite island, which form first during solidification. Here, greater solubility for the impurity than the constituent which form later. The presence of ferrite also means that there are more interface boundary available to reduce the low melting grain boundary. The presence of ferrite increases tensile strength. High ferrite content may improve resistance to trace corrosion cracking. Conversely, the ferromagnetic Ferrite phase may interface in application requiring well metal with low magnetic permeability, such as vase, time-on magnetic, main sweeper, and certain control pad in nuclear reactors. Ferrite present in relatively continuous network decrease corrosion resistance of the molybdenum contained well metal in certain environment. Long-term creep strength may be lowered in parallel ferrite weld. During welding itself, shrinkage during exposure in heat treatment in service to temperature in the range of 1100 to 1700 degree Fahrenheit, 590 degrees centigrade to 925 degree centigrade or lower. Weld with high ferrite content become imbrittle through formation of the sigma phase, a brittle intermetallic microconstituent. Sigma reduce the ductility, impact strength, and corrosion resistance of the weld metal. Ferrite lower energy absorption at cryogenic temperature. Measurement of ferrite. It is difficult to accurately determine how much ferrite is present in stainless steel weld metal. The advisory subcommittee of welding stainless steel and the high alloy committee of the Welding Research Council have attempted to resolve the problem by establish an arbitrary standardized value known as a ferrite number Fn to designate the ferrite content of austenitic stainless steel weld metal. Therefore, the ferrite content should be specified and measured in terms of ferrite number. A ferrite number not necessarily a true absolute ferrite percent, but below 10 Fit is very close to the actual ferrite content. There is general agreement between laboratories when measuring ferrite using the new standard technique and the ferrite number. As standard procedure for calibrating magnetic instrument to measure the delta ferrite content of austenitic stainless steel weldment, AWS A4.2 standard procedure for calibrating magnetic instrument to measure the delta ferrite content of austenite stainless steel weld metal has been published by American Welding Society. Why important of ferrite? Fine structure cracks commonly occur in full austenitic weld metal strain 20% as in bend test. Hot shot cracks are seen heavily restrained weld. Now ferrite can be measured constantly in ferrite number. Researchers have found that delta level of at last 3 Fm will eliminate fine surface cracking in the weld metal with the commonly used austenitic filler metal E682. E316L, 308, E3016 and 308L. A ferrite level 4Fn is required, E309 5Fn with E3018 and 6Fn. E347 will assure freedom from cracks. Type 308 filler metal may also be designated to produce well metal containing ferrite, which help prevent hot cracking. Type 310 well metal, on the other hand, is fully austenitic contain ferrite and thus in more susceptibility to hot cracking. Type 316 and 370 filler metal may also be designated to produce well metal containing ferrite. For this reason, and possibly because some beneficially influence on the molybdenum, their cracking resistance is satisfactory. The corrosion resistant partially ferrite well metal produced from type 316 317 may require special attention under certain conditions. Any 18 chrome 12 nickel molybdenum well metal, including type 316A and 318, may display poor corrosion resistance to certain media in as well condition. Such poor corrosion resistance, which is manifest by highly localized attack on the ferrite, does not occur in all media, more does it under all discrimination, under all circumstances. It seems most likely to occur when the certain hot oxidizing acid are present. Preventive measures are to annul to the joint after welding or just the composition to eliminate any ferrite in the weld metal. Type 347 filler metal is usually formulated to produce a larger amount of ferrite in the weld metal as a means of suppressing cracking. Ferrite particularly helpful in this alloys because chromium in the quantities used in this steel promotes cracking in fully austenitic weld metal. Weld metal from E310 CB electrode is selected for particular application would require special consideration. This is no possibility of obtaining any ferrite at all from the composition, and the weld metal may be specially crack sensitive. Electrode of E1682 containing approximately by 16 to 8% nickel and 2% molybdenum are used primarily for welding type 360 stainless steel when employed in high pressure, high temperature piping system. The weld metal has good hot ductility, which offer greater freedom for use metal heat affected zone cracking under condition of restraint. The weld metal also has excellent mechanical property in either the as well or solution treat condition. The control of ferrite in root pass and subsequent pass. The control of weld cracking by introducing delta ferrite in the weld metal requires of the weld metal composition. The weld is formed from the base metal and the filler metal. Dilution of filler metal by admix or flux or nitrogen absorption from the atmosphere alter the composition of the weld metal from the original filler metal composition. Dilution may be 50% in the root pass, a shielded metal arc welding, SMAW, or gas tungsten arc welding, GTAW, pipe welding. As an example, if the pipe weld metal has no ferrite or even an excess of austenite forming elements, the filler metal will need 6 Fn or higher to produce weld metal with 3 Fn. Also, a consumable insert is implied should have a sufficient ferrite 11 Fn, for example, withstand the dilution obtained with the parent metal when making the root pass of the weld. Root pass, so the weld will contain at last 3 Fn. Nevertheless, the determined effect of ferrite in high temperature and cryogenic application and in certain corrosive media dictate as upper limit on the amount of ferrite to be permitted. Therefore, extra delta ferrite should not always be added just to make sure there is plenty of ferrite. In practice, the control of ferrite being by specific acceptable ferrite number range for filler metal. Effect of welding condition. The AWS Advisory Committee of Stainless Steel conduct test program to determine the consist may be delta ferrite obtainable in weld metal from the same box of weld electrode. With each laboratory checking on other laboratory and using prescribed welding condition, each laboratory produced weld pads that had 95% the Fn reading between 4.8 and 7.2 Fn for welding electrode with a mean of 6 Fn. The weld pads were tested according to AWS 4.274 procedure. However, the method of making a weld alter the ferrite content of the weld metal. The test condition by advisory committee study for weld pad produced an electrode producing weld metal of 6 Fn yielded 5.1 in one normally procedure and 7.6 in another. Chemical composition of weld bed, and therefore its ferrite content will be noticeably modified by such variation as a long arc rather than short arc, welding an exposed weld face pass rather than a protect D groove, and welding with turbulent aspirant shielding gas flow rather than with smooth inert gas shielding, melting the root face of the groove weld. Compared to the multiple bed of subsequent layer in the some groove will noticeably vary the percentage deduction of the filler metal by base metal and so will affect the ferrite content. Example, variation may cause as much as 5 to 6 FM change either pulse plus or minus. However, the ferrite number resulting from such larger variation can be measured and used as a first step toward correcting the technique. Effect of welding condition of ferrite. Good welding procedure require testing. Planned, weld assured adequate but not excessive ferrite content. Adhering to such a procedure and using the same lot of filler metal will give the same planned weld metal within about plus minus 2 FM. Excessive delta ferrite has been shown determined to both high temperature creep resistance and low temperature toughness. A well planned test program consulted with the reliable filler metal producer are recommended for critical application. Thank you.